Computing the derivatives of circular functions, and by that I mean of course trig functions, is as easy as the derivatives for hyperbolic functions because we have some formula. However, in the case of hyperbolic functions, the formula we had were the formula that defined the function itself, and we used those and the exponential rule in order to arrive at the formula we needed. In case of circular functions instead, what we're going to be using is we're going to use a limit formula that we have figured out earlier on. Okay, so what we're going to be doing is do the following. This is the plan for how to figure out derivatives of circular functions. First of all, we're going to use the limit definition for y equals sine x and y equals cosine x. And within that limit definitions, we will find those formulae I mentioned that we already have and that we can use. Then we're going to use differentiation rules for other basic functions like tangent, cotangent, and so on. And finally, we're going to use implicit differentiation for inverse functions. So if we're going to look at the derivative of the inverse sine or the inverse cosine, we're going to be using implicit differentiation as we have seen in the past. After we've done this, then we can handle combinations of trigonometric functions combined with polynomials, with exponentials, with hyperbolics, and whatnot, and whatever other combinations we want. All we have to do is use the appropriate rules. Now, I'm not going to show you each of these strategies. I'm going to show you one example for each of them, and then we're going to see some more in class, and then hopefully you will do a few more on your own. So let's start from figuring out what the derivative of cosine x is, okay? And follow carefully because the derivative of sine x is obtained exactly in the same way, just a few changes in the formula that we need. So how do we start? Again, we use the limit definition. So we start by saying that the derivative of cosine x, by definition, is the limit as h approaches 0 of cosine of x plus h minus cosine x all over h. Well, unfortunately, this formula as it stands does not have anything that we can use in terms of factoring. The subtraction might suggest the use of some kind of a rationalization, but it actually doesn't work that way. If we rationalize by multiplying by the conjugate, we'll basically get into a dead end. But what we can do is we can use addition rule for cosine. You may remember from high school, or maybe from the review you have done at the beginning of this year, that the cosine of x plus h, or the cosine of a sum, can be written as a formula which involves only cosine x, cosine h, sine x, and sine h. So it untangles the sum. We're going to end up, of course, with a slightly longer formula, but hopefully the untangling will work. Now, if you don't remember what that formula is, you can go and look it up. Feel free to pause the video here and go look it up on your own. Even if you're lazy in a teasing sort of way, here is how it works. The cosine of x plus h is going to be given by the cosine x cosine h minus sine x sine h. Well, at this point, we almost have what we need in the sense that at this point, we actually have some common factors. Notice that those two terms in the numerator both have a cosine x, and we can try to factor it out and see what happens. If we do that, we end up with this expression now. So the cosine x has been factored out, and we're left with the cosine h from the first term and a minus 1 from the second term. And then we have the other piece. At this point, it may still look like we have just a longer formula, not necessarily better. But if you remember, some of the limits of trig functions that we have seen in the past were almost there. Because what we can do is, first of all, we can split that fraction. There's nothing else we can do in terms of combining those two terms, so we might as well split them. So we end up with the limit as h approaches 0 of, first of all, cosine x times cosine h minus 1 all over h, and then minus sine x sine h over h. But now notice that in the first fraction, the cosine x does not depend on h, and in the second fraction, the sine x does not depend on h, which means we can take both of them outside of the limit. So what we can do is we can take the cosine x, move it out, and then be left just with the limit as h approaches 0 of the remaining fraction. And then we can do the same thing with the second one. The sine x can go outside of the limit because it does not depend on h, and we're left with that limit. Now, the second limit, hopefully by now, is very familiar to you, and once you recognize that one, you should be able to recognize the first one as well, because they're the two basic trig limits, and certainly the second one is. So let's see what happens. Cosine x, well, we've taken it out, but there's not much else we can do, and the limit as h approaches 0, cosine h minus 1 over h, we saw earlier that is actually equal to ta-da! 0. Okay, so that's nice because that's going to cancel all that stuff on the left. As far as the second piece is concerned, the sine x stays, and the limit as x approaches 0, sine h over h. I hope by now you know it by heart, and that, of course, is equal to da-da-da, 1. Okay, well, I'm exaggerating with these ta-das, haven't I? All right, but anyway, the first piece cancels. The second one is just multiplied by 1, so all we're left with is the familiar fact that the derivative of cosine x is negative sine x. You can use, again, I do encourage you to use the same technique to figure out what the derivative of sine x is. So let's see now how we can compute derivatives of other basic trig functions. I'm going to show you how to do secant x, and then of course the same method will apply for tangent and cosecant and so on. Now, in this case, what we're going to do is we're going to use the defining identity for secant x. You may remember that secant x is actually going to be given by 1 over cosine x, which means that the derivative of secant x can be computed from the derivative of 1 over cosine x. And now we're computing the derivative of a quotient, so we need the quotient rule, and in the quotient rule we're going to have to use the derivative of cosine, which we just figured out. So let's apply the quotient rule. What do we get? 1 prime, that's going to be 0 times cosine x minus cosine prime. We know what that is. That's negative sine times 1 all over cosine squared. So once we put together our knowledge, the first term becomes 0. The second one becomes just a negative sign with the negative, which is part of the function. It becomes just sine x over cosine squared x. We could stop there, and we could say that the derivative of secant x is sine x over cosine squared x. Tradition has it, however, that we don't do that, and we're going to do a little bit of changes. We're going to write that fraction as 1 over cosine x times sine x over cosine x. So in other words, we're going to factor the denominator into cosine x times cosine x. And now we recognize the first fraction as the original secant and the second one as tangent. And so we now have the familiar formula, again familiar if you saw it in high school, that the derivative of secant x is secant x times tangent x. So once again, I encourage you now to try your hand at doing the same thing on tangent x and cotangent and so on and so on. We're going to do some of those in class, but it doesn't hurt if you do it yourself. Especially maybe if you can throw in some extra complications like, I don't know, secant of 2x maybe? Yeah, well, that's an idea. What about other trig derivatives? Again, so if you try your hand at them, you'll find out that the derivative of sine x is cosine x, as you remember from high school. The derivative of tangent x is secant squared x, if that's what you find by using those rules as I've shown you. The derivative of cosecant is minus cosecant times cotangent. Again, check that you get the right answer. And the derivative of cotangent is going to be minus cosecant squared. Again, check that you get the right answer. What I want you to do is that to prove again each of them, and also if possible memorize them. It's not an absolute must, but certainly the more you can memorize, the easier it's going to be once you have to deal with more complicated functions. If you don't have to look up or even worse prove these formulae each time, it's going to be a lot faster. Alright, so what about derivatives of inverse trig functions? As I mentioned at the beginning of the video, what we're going to do is we're going to use implicit differentiation. But before we do that, I want to remind you of a couple of things having to do with the inverse cosine. First of all, remember that the domain of the inverse cosine is not it needs a certain restriction. Actually, the domain of the cosine function had to be restricted in order for us to get the domain of the inverse cosine. And the domain of the inverse cosine is going to be the range of the cosines. That means that our x has to be between -1 and 1. And what is the range? Well, the range is going to be the restricted domain of the original cosine, which, if you remember, was between 0 and pi. And you might say, what do now domain and range have to do with derivatives? Let's just compute it. Well, there's one step where we're going to need this formula. Okay, so hold on to your hat. So at this point, we're going to use implicit differentiation, and the whole idea is, well, let's get rid of that inverse function by applying the original function cosine on both sides. So we're going to apply cosine to both sides, and that gives us cosine of y is equal to x. Now the right hand side has become very easy. The left hand side is not as easy, but it's also easy and in fact possible, because we know how to compute the derivative of cosine now, and we can use the chain rule. That's the whole idea behind implicit differentiation. So the derivative of cosine is going to be minus sine y times the derivative of the inside, which gives us y prime, equals on the right hand side is just the derivative of x, which is 1. Alright, now let's solve for y. That's fairly easy, and it turns out that y prime is equal to minus 1 over sine 1. Yay, we're done. Not quite. Remember, we want y prime as a function of x, not of y. So what we need to do is try to do something to get rid of that y in the denominator. So at this point, it looks like we're done, but not really. We're not really done, because we're still working in terms of sine y. And we want to have our answer in terms of x. Okay, so what we need to do is we need to change our y back to x, and you can tell that we're going to use the original function, but let's see how that is done. This is in fact where we're going to be needing the information about domain and range. What we want to do is we want to rewrite this expression in terms of x, and we can notice that the range that we're dealing with for our cosine, inverse cosine function is between 0 and pi. In other words, our y has to be between 0 and pi. But if y is between 0 and pi, that means the sign of y is always positive. That's because if y is between 0 and pi, it means we're on the top half of the unit circle, and therefore the sign is positive. Well, if it is positive, then I can write that sine y is going to be equal to the square root of sine squared of y. And now I can use the basic Pythagorean identity for trig functions and say that, well, that sine squared of y I can write as y minus cosine y squared, or cosine squared y. But remember, what was cosine y? Well, cosine y is our x. That's how we were working with. Y is inverse cosine of x, which means that the cosine of y is equal to x. And therefore, the derivative of the inverse cosine is negative 1 over square root of 1 minus x squared. Now we're done. Now we have our function in terms of x. But look at the surprise here. We started from a function which was the inverse of a trigonometric function, and what do we come up with? An algebraic function. Okay, something which does not have sines, cosine, tangents, or anything else like that. Just a simple square root and some squares. Okay? So once again, what I would like you to do is try your hand and doing the same thing with inverse sine and inverse tangent and so on. We're going to do some of them in class, but well, actually, when I say we, I mean you will be doing some of these in class under my supervision, but try them at home to begin with. Alright, now once we have all these derivatives and we have formula for both the derivatives of trig functions, their inverses, then we can combine all of these things together and compute things like the derivative of secant x over cosine of 3x. Well, how are we going to do this one? Well, of course, it's a quotient, so we're going to start by applying the usual rule, which means, first of all, the quotient rule. Alright, so quotient rule means we're going to end up with a quotient. On the numerator, we're going to end up with the derivative of secant, which is secant tangent. We saw that earlier. And then times the denominator, which is cosine of 3x. And then minus the derivative of the denominator, the numerator, secant x, times the derivative of the denominator, which is going to be minus 3 sine 3x. Where is that extra 3 coming from? Well, of course, the chain rule. We're taking the derivative of cosine of 3x. The derivative of cosine gives us the minus sine of 3x, and then once we go inside, we get the derivative of 3x, which is just 3. And in the denominator, we just have the cosine squared of 3x. And that's the derivative of that function. Now, of course, you can beautify this thing to your heart's content, but that's it. That's the derivative. Unless we know what else we need to do with that derivative, no need to do any simplifications. So, time for you to practice on these things, review whatever it is that you need to review, and the rest is going to be just fun.